This lab exercise is to explore the hydraulic jump phenomenon. The objective is to learn what the hydraulic jump is and be able to properly create and measure a jump. Before we start the lab exercise, we must first learn a few definitions. The first important definition is critical depth. The critical depth represents the depth representing the minimum energy. Critical depth is dependent only on the flow rate and the geometry of the channel, as shown in the equation. Using the critical depth, we can classify the flow. The first classification is supercritical flow. The flow regime is supercritical when the flow depth is less than the critical depth for the given flow rate and channel geometry. Supercritical flow is generally associated with steeper slopes and mostly occurs in man-made channels. Some examples of supercritical flow are flow in street gutters, flow down a spillway, or flow in steep concrete channels. The second classification of flow is subcritical flow. The flow regime is subcritical when the flow depth is greater than the critical depth for the given flow rate and channel geometry. Subcritical flow is the most common type of flow and is a result of smaller channel slopes. Most natural channels have subcritical flow. With these two flow regimes now defined, we can define the hydraulic jump. A hydraulic jump occurs when a zone of supercritical flow discharges into a zone of subcritical flow, causing the depth of water to cross critical depth. The transition between the two flow regimes is associated with a large amount of energy dissipation. Common locations of hydraulic jumps are spillways, where the spillway discharges into the natural channel. It is of interest in engineering to know the ratio of flow depth across the hydraulic jump. This ratio can be computed by momentum conservation across the jump, as shown in the equation. We are now ready to go into the laboratory and create hydraulic jumps using a hydraulic flume. Protective clothing is a good idea, but not required for this exercise. Before we start the flume, the hoses must be checked for loose connections to prevent leakage. You can now start the pump and set the flow rate. The flow rate may be roughly adjusted to the desired flow rate by using the flow rate gauge below the end of the flume. For an accurate reading of the flow rate, use the hydraulic bench and stopwatch to read the volumetric change of water over a defined time interval. We can now set the slope on the flume to create the desired normal flow depth. Since we know the flow rate, we can calculate the critical depth for this flow rate, given a channel width of 76 millimeters. To help us create the hydraulic jump, we can mark critical depth on the side of the flume and use it as a reference point for supercritical and subcritical flow. In this case, we see that the flow of water in the flume is at or near critical depth. Take a moment now and think of ways the hydraulic jump could be created in this condition. Since the flow is near critical depth, we can use the stop logs at the end of the flume to create subcritical flow. Now that we have subcritical flow, we need to force supercritical flow upstream. This is done by inserting a sluice gate and setting it to the desired level. The sluice gate will back water up behind it. Check to make sure the water level doesn't get too high and start leaking. We can now verify the height of the jump by first taking a measurement of the upstream depth, or the depth in the supercritical section. Using this depth and the flow rate, the depth downstream of the jump is calculated. This can then be verified with measurement. We are going to increase the slope. Take a moment and decide whether the critical depth line should be raised, stay the same, or be lowered. You're right, the critical depth does not change since it is only dependent on the flow rate and geometry, and neither was changed. We can see that increasing the flume slope has decreased the normal flow depth, such that we have supercritical flow. Since we already have supercritical flow, all that we need to do in this case is cause subcritical flow downstream. This is done by inserting stop logs at the outlet.